Hillslopes are the single most widespread landform on Earth, and they are covered with soils often. They can be covered in vegetation often. And they can include both bedrock and soil mantled slopes, and they can also be made of sediments, things like sand or silt from either windblown dunes or loess. So as our first example of hill slopes, we're just looking at one right here that's in southeastern Minnesota, close to Winona. I think I took this picture back visiting one of my best friends at college in 2009. And it was right around Thanksgiving. And so all the leaves are down, and you can see that there's a very kind of straight, linear slope to this hill. And you can see that many of these trees are actually kind of tilting a little ways down the hill slope itself. And so the trees are actually being rotated as the soil moves beneath them as it creeps down slope. And then at the top we have this cap rock, which is lying atop the bluffs, forming the plateau on which much of the agriculture of the region is founded. And this limestone is cropping out just to the right, on the right-hand side of this photo. So the idea behind this lecture is to give you a little slideshow looking at a number of hill slopes and to start to think about the processes that shape them. And in particular, we're going to talk about creep, which is the slow, gradual motion of particles of whatever the hill's made out of. It could be soil, it could be sand, going down slope, as well as mass wasting events, things like rockfall and landslides that rapidly change a landscape. So, in landscapes, like I mentioned, in most landscapes, you have two dominant landforms. Hillslopes, which cover almost the whole surface, and channels, which don't cover quite so much, but impact hillslopes. And so if you look at this Google Maps screenshot, this is just the edge of West Virginia near its border with Ohio, and you'll notice that the channels, these little blue things, or sometimes not even blue things that are between the ridges and the low areas, don't occupy a huge portion of the land. However, what they're important for is affecting hillslopes by eroding material away and causing hillslopes to become steeper. Or sometimes a hillslope will send enough material through a channel that it will fill it in. So we have hillslopes and channels in this landscape, and there's some other landforms as well. There are things like floodplains, which you can see there along the Ohio River on the kind of western side of this image. So north is up in this image. And so there are both floodplains and river terraces, which are ancient abandoned floodplains. And then on top of that, there are glaciers and lakes and dunes, which can act as hill slopes and coasts. And so there are a number of other things we talked about back in the geomorphic process domains section. And so when we think about, floodplains, we can think of them as either part of the channel if they're being flooded, or as part of the hill slope if they're actually actively undergoing hill slope processes. And that sounds a little self-defining, but what that means is whether there are landslides coming off the floodplains, whether there's soil creep occurring on the floodplains. And like I mentioned way back when we were doing the process domains, one of the main reasons we create these is just for simplicity. Obviously, there are going to be landforms that kind of combine both or transcend these simple definitions, and so let's just bear that in mind as we go through all of this. So hillslopes can be very diverse, right? So you can have bare hillslopes or vegetated hillslopes. Those of us like me who are from the Midwestern U.S. are really used to hillslopes being vegetated. But if I go out to the Western U.S., I'll see these desert regions with, high spires and buttes, and all of those might have very little vegetation on them, if any. And the same deal if I go into Badlands regions, like in Badlands National Park in South Dakota, or in Utah, or in North Dakota, or in many other areas of the world in which Badlands form. So hillslopes can, as I was mentioning, be related to slowly creeping soils or rapid mass wasting like landsliding. They can be made of different substrates, so things like glacial till, bedrock, or sediments that form layers. Their slopes can be steep or gentle. And there are some that are in what we call steady state, and some that aren't. And we're going to talk about topographic steady state a little bit later in the class, but the question here is is there as much material that's coming up through weathering of the soils at the bottom? So is there enough new weathered material turning from bedrock or from whatever parent material it is into soil to replace the amount of soil that's being lost via hillslope creep or mass wasting processes? And this will affect the hillslope's form, and this will combine with the soil production functions to determine what the equilibrium soil thickness is on the hillslope. And you can imagine that if the hillslope soils are very thick, then that might relate to pretty slow lateral soil motion away from a section of the hillslope. Whereas if soils are very thin, it might mean that that section of the hillslope is shedding soils all the time. So I'm going to talk a little bit about hillslope processes here, and here is just a quick figure on the right. So we're looking at an incised fill terrace, and this is in northwestern Argentina by the indigenous community of Isla de Cañas. And my friend Steffi Tofelde, who's about 170 centimeters tall, is standing sort of straight, sort of not out there, sampling a layer for geochronology, so in order to perform a dating method to be able to figure out when this fill unit deposited. And we're taking advantage of this gigantic pile of rocks, and so you can see this big pile of rocks that she's standing on. All of that came from up above and formed this cone right here. And so this sort of rockfall processes that form this sort of cone, that's one example of hillslope processes. And in general, hillslope processes can be summarized as things move downhill, whether they're big rocks, little rocks, or soil. Typically, big rocks move downhill in bigger landslides. Soil moves downhill through slow creep. And soil can form through chemical and physical processes. And although we don't often think about this in weathering, many of these processes can be biologically mediated, whether we're talking about, sort of very small scale, like catalysts, so thinking about things like biological catalysts, enzymatic catalysts for chemical reactions, or for larger scale processes, so things like, let's say, a whole bunch of ungulates running across a hillslope, pushing down the soil, or burrowing animals, fluffing the soil up and throwing it downhill. And some hills, that English isn't very good, but, sometimes there are lots of things that move on hills, and other soils and hills just weather in place. And I'm hammering this home because it's important. There are two main processes that move hillslope material. One of them is creep, that creates smooth landscapes typically, and the other one is mass wasting, which is sudden rockfall landslides and creates really rugged landscapes. All right, let's start looking at a few places. So this is a region in China that's very well known for its karstic topography, so a lot of dissolution-related weathering, and there are these really steep spires, and there's almost no soil on the spires. So when you look at them, you think about how they evolve, and if it's not just dissolution, which is gradually causing the removal of material, it's mass wasting. It is rockfall off of those, and you can see those forested zones at the edges of the hills. Well, based on the farms around it, people are farming basically everywhere they can, and those forested zones are kind of steep, and so those seem like aprons that are being built up as those pillars of rock are weathering away. And as those aprons form, vegetation colonizes them. There are cracks between the boulders and debris that they can stick their roots into and start drawing up water. And on top of that, they're just dangerous to be around. Although, based on the fact that there are some trees and those trees seem to have reached maturity, it seems that major rockfall events here must be, kind of fewer and farther between. But sometimes you just don't want to risk it. The other thing about this apron is that you notice it doesn't cross the entire landscape, right? There are these flat fields, and so we know that there must be something else here, maybe a river moving material away physically, or maybe there's just gradual dissolution of these broken down boulders and broken down limestone boulders that removes them over time, and that's what causes the flattening of the landscape. I'm actually not so familiar with this region, but it looks like a completely gorgeous place to see. This next example, and sorry for the slight fuzziness of this photo, is from the Sandhills in Nebraska. And you can see this road, kind of this ribbon, just bumping up and down and rolling along. Well, the Sandhills are a place where there were once sand dunes that were active during the last glacial period. they're now vegetated and stabilized. And so they are no longer evolving quite so much through blowouts, although there are some locations where they become unvegetated and the sand starts blowing around. And instead, they've started to smooth out through hillslope processes, and because they're mostly just sand and that's quartz, that's really chemically inert. So the primary hillslope processes that are causing them to evolve are related to physical activity, like freeze-thaw cycles, and biological activity, but acting physically on these hills. So think about animals running across them. These areas used to be patrolled by herds of bison all the time. And of course, some part of the upper layer of the sandhills is actually held together by cohesive organic material atop the soil, which has formed over the years and centuries and millennia of vegetation of these surfaces. Here's an example from the Nature Conservancy of southeastern Minnesota, and you can see this transition between a hill and a channel with a floodplain. And so you can see, if you look in kind of the lower right quadrant of the figure, this channel moving through its flat floodplain. The flat floodplain tells me that the river has moved laterally to bevel off a surface, and or that it has aggraded, and so it used to have a lower valley, and it filled up the region underneath it. And I'm guessing that in this region it's more option B, although option A is probably happening as well, because it really looks like that hillslope just plunges straight down into the floodplain. It doesn't smooth out so much as it gets towards the floodplain, and so it really looks like the bottom of the hill is just swimming in fluvially deposited, by which I mean river deposited sediment. Those hills are fairly steep, which also tends to tell me that their erosion is ongoing and or has been recent. And because I know that southeastern Minnesota isn't tectonically active, I know this region isn't uplifting. So this is most likely related to some sort of river reorganization or recent pulse of erosion in this otherwise fairly stable, what we call cratonal, so stable continental crust landscape. And this is just another example. I believe I took this photo. That's probably why there isn't an image credit on it. But that's just showing us the above this roof that we see, these sort of steep sections, and we're looking across a valley over to a farther hilltop. But it's just another example, one of my photos of that same region from the ground. And same region again, we're looking across this hillside, and you can see that this is a fairly steep hill slope. These trees are sticking out of it at an angle, and by assuming that the trees are trying to grow straight, if you look at trees with relatively straight trunks, you can kind of draw a line and kind of think, okay, maybe that's 25, 30 degrees. I'm just eyeballing it, so if you have a protractor, you're going to be better than me. But these hill slopes are rapidly moving material if they're that steep, right? Because there's going to be a lot of gravitational, component of gravitational force pulling stuff down the hill. And if you get a lot steeper than what we're just seeing here in Minnesota, here at least where I am, obviously I don't know where all of you are, we can have landsliding. And so here in New Zealand, these landslides are crossing the road. And this is a photo from 2016. And New Zealand, unlike the upper Midwestern US, is experiencing rapid tectonic uplift. That rapid uplift of material pushes one block higher than another, and they might be adjacent. And what that then means is that there are steep slopes that are generated by tectonic uplift, and so it's tectonically active areas where we often see very rapid river downcutting because of those steep slopes, and so the rivers are easily able to slice through that landscape because they have a lot of power. Their gravitational potential energy is being converted to kinetic energy really quickly. And also on hill slopes, we have steep slopes that don't just fail via gradual soil creep, but they actually reach their elastic limits and start to break apart and fall down the slope as these landslides. And while it happens, primarily in tectonically active areas, here's a photo of me from August 2012. It's now 2020 while I'm recording. I certainly look younger there, but fortunately no less handsome. And this is after major floods hit the area around Duluth, Minnesota. Thanks to Francis Rengers from the U.S. Geological Survey for this photo. We were scouting around and hiking on the Superior Hiking Trail after a paddle into the Boundary Waters. and found this. Francis actually works on landslide and wildfire hazards at the USGS, so it's very appropriate that he took the photo. And this whole set of erosion is a failure that's in former proglacial lake deposits from the proglacial lake that once occupied the Lake Superior Basin when the large ice sheet, what we call the Laurentide ice sheet of North America, was present towards the end of the last glacial period. So these lake sediments, all just clays, saturated and failed. And in fact, I just went back to this exact same site last year in 2019. Don't have a photo of that right now, but I might want to share that with you guys at some point. You can ask for it and see how much older I do look. And what I can show you there is that this whole region of clayey soils actually has not revegetated. And so I've been meaning to ask an ecologist about why that is, whether it's just very difficult for plants to become established there, whether the erosion has persisted. And that's important because this bare soil can be a large source of continued erosion and sediment because there isn't a cover of vegetation intercepting rain and protecting it. Here's another example, Pumpkin Buttes in Wyoming. There's a flat top mesa of cap rock on the top that you see, and then you can see this, and that's an erosion resistant rock unit, and it's protecting the less erodible unit underneath it. And I think this might be the last one. So this is a lovely photo by this guy, I'm forgetting what the rest of his name is, Dale, from Sioux Falls. This guy actually sells his photos online, so I feel like if I'm using his photos, you should, and you really, really like it, I should give a plug for it. And you can go and purchase them from him. But one thing that I really love about this is that unlike Pumpkin Buttes, where we see this large cap rock layer, in this area of South Dakota, we instead see this very roly-poly landscape, very rounded. And so you can think about the fact that if I go back to this, that in Pumpkin Buttes, that cap rock is probably eroding through some sort of large mass wasting process at the top, where it's failing in blocks, whereas the rounded stuff underneath it might be gradually creeping, or maybe sometimes landsliding. It looks like it's pretty steep. And in this other case in South Dakota, what we're seeing is the fact that this landscape, which is underlain, I believe, by Pierre shale, so a shale unit, fairly erodible sedimentary rock deposited in the Western Interior Seaway. If you're really into paleontology, you should look that up. Is creating these nice rounded hill-shaped forms that are really characteristic of gradual hill slope creep. So why do we want to study these hill slopes in the first place? Why do we care about these different forms and the processes? Well, first off, from a scientific point of view, there's a whole diversity of forms to understand. And it's also the place, from a more practical standpoint, where most of us live or farm or, eat food from those farms and work. They're the landform that supports fields, forests, plains, and deserts, all the places that at least I like to run around and explore the world. If you're more of a city person, well, you know what? Cities are kind of armored hill slopes covered in houses and streets and so forth. The mass wasting events, including landslides, are important natural hazards. Both mass wasting and hill slope creep deliver sediment to rivers and watersheds, and they form soils. And so if you guys have read any of Dave Montgomery's books, like Dirt, or from looking at his Nobel Conference presentation at Gustavus Adolphus, you might know a little bit about just how important soil formation is to sustainability and to, in general, our ability to ensure that we have a fed, healthy global population. So in the future lectures, we're going to be going into the specific processes and mathematical representations of the processes. The point now is really to just give you this first pass idea of hill slopes, what they are, what they look like, their diversity, and to appreciate them and start thinking and imagining a little bit about how they form and change.